All right, welcome back to our final gas law video. We're going to be ending by talking about ideal gas and the ideal gas laws. So to be an ideal gas, the gas has to be what we would call ideal, right? It would be under ideal circumstances. Those criteria are what we have here. So the first is going to be random motion. So the gas, while it's moving around inside the container, is going to be randomly moving in any direction. There's not some guy with a steering wheel deciding where the gas molecule is going. It's completely random and will continue to be completely random after it collides with other molecules or it collides with a wall or whatever type of container that the gas is in. Elastic collisions means that when the gas molecule collides with another gas molecule or the wall, it doesn't lose energy as it does so. So what happens is, let's say we have this gas molecule going that way, and we have this gas molecule going this way. What's going to happen is they're going to collide, so like that, and then they're going to go off their separate ways back in the other direction. And what an elastic collision means is there's no energy loss here. So we're going to assume that no forces between these gas molecules happen. So we're going to say there's no attraction or repulsion from each other. They're just going to hit and bounce off. This doesn't absolutely happen, but we're going to assume for a gas to be ideal and do our calculations that there's no energy loss when these gas molecules hit the container or hit each other. This isn't true most of the time, but for the sake of doing equations, we're going to follow that there's no energy loss for that. Occupying a small space. So this is so that the mass is negligible, so we can ignore the mass of a gas molecule because often it's very, very small, right? It's because we can't see it. So we're just going to ignore the mass. So we're going to say it takes up a very, very small space. And as we know, most of gas is just empty space rather than the particle. And then the last one is that it obeys all the gas laws. So the gas laws we've talked about already with Boyle's, Charles, and Gay-Lussac's law. These gas molecules will obey those laws that we've seen already. Okay, so those are the requirements for an ideal gas. When we talk about an ideal gas, we have an ideal gas law. And this ideal gas law is created by combining the gas laws that we've talked about already. So the ideal gas law is going to be P V equals N R T. Okay. When we look at this, P is going to be our pressure. V is going to be our volume. N is going to be the number of moles of gas that we have. So moles is another word for how much of a substance we have. It's like saying we have 3 dozen eggs, or we have 3 moles of oxygen. Okay, it's just another word for quantifying how much that we have. It's a unit of measure, which we'll talk about in a later section. But don't get caught up with it now. It's just going to be a number. So it'll say like 3, 4, 5, 6 moles of gas. That just says like, okay, we have 6 gallons of milk. It's just another word for saying how much we have. R is going to be a gas constant. So we need a constant in order for this equation to work. We're going to be using the gas constant that is in the units of liters ATM per moles Kelvin. So the R is going to be 0.082, and I'll move the screen over so you can see that. R 0.082, and the units for this are liters ATM per mole Kelvin. Back up before. Okay, so R is going to be 0.082. There is another R that does exist. It's in kilopascals. We're not going to be using that. So if you Google gas constant, it is not going to show up as this. We are using this one due to the units that we have. Okay, and temperature, well, that's T, right? Temp. Okay. When we're using this gas constant R, we need to make sure that all of the units must match R. All units must match. So in order to use this R in our calculation, They have to match what is given here. So our volume has to be in liters. Our pressure has to be in ATM. We have to have moles in moles, which we always will. And our temperature has to be in Kelvin. Okay, we can't use Fahrenheit and we can't use Celsius. In order to use this gas constant, it has to be in Kelvin. So you need to make sure that when we are doing our calculations, that all of our units are matching what R is going to be. Because if we don't, we won't get the right answer. We have to have it in this format. And when we have our units in this format, they will all cancel out and only leave the one unit that we're solving for. Okay. There's one thing we haven't done yet, and that is talk about switching between different temperature scales. So if we look at this little diagram, we have the conversions between Celsius, Fahrenheit, and Kelvin. So we use Fahrenheit, which is a good scale for temperature. Celsius is the next unit for temperature that we see the most often. Most of the world uses Celsius, so we're kind of on our own out there. Kelvin is the scientific temperature. So we use Kelvin because we can sort of mimic an absolute zero with Kelvin. Kelvin is going to be degrees Celsius plus 273.15 for being exactly accurate. So this diagram isn't as precise as I would like it, but if you use 273, that's good. But please note that if you're doing this 100% correctly, that this should be 273.15. So if we're going from degrees Celsius, from Kelvin to Celsius, we do the Kelvin minus 273.15. That's our degrees Celsius. If we're going from Celsius to Kelvin, we would put our Celsius degree in here and then add 273.15, and that'll get us our answer. And then when we're solving between Celsius and Fahrenheit, that's just kind of a nightmare. If you want to use these equations to do that, that's fine. Or you could just put it into Google, Celsius to Fahrenheit conversion, and type it in. That's what I do. I'm not going to ask you to sit here and convert between Fahrenheit and Celsius because guess what? You're not going to need to do that for the rest of your life. So we'll just call on Google to do that. So you feel free to just type it in there because that's what I do anyway myself. Okay. So these are the equations we'd use to convert between temperatures. If you need it, please pause the video and copy those down, and we'll move on. So we'll go to our last problem with an ideal gas. Let's zoom in so we can see it. There we go. If there are 4 moles of gas at a pressure of 5.6 atm and a volume of 12 liters, what is the temperature of the gas? So before we even start, let's put the information we need at the top. So we know that the ideal gas law is PV equals nRT. We know that. We know that R is going to be 0.082, and R is going to be in liters times ATM over mole times Kelvin. Okay, so we know that we need these units. We know that R is 0.082. We know our equation is this. Now we're ready to start. So we'll do the same thing we did with the previous gas laws, is we'll read the problem one by one and assign numbers to variables. So if there are 4 moles, so moles is going to be Rn. Our pressure is 5.6, so that's going to be P with ATM. Volume is 12 liters, that's V. And what is the temperature? So we're solving for temperature. We don't know what that is. So we assigned 3 variables. We know R is a constant, so we only have one thing we need to solve for. So we'll just plug these numbers into our equation and see what we get. So P is first, so we have 5.6 ATM. Then we have our volume, which is going to be 12 liters. That is going to equal N, which is 4 moles, times R, which is 0.082 liters ATM per mole Kelvin. And then we have times our temperature, which we don't know and we're going to solve for. So when we have the equation lined up here, you can sort of see why the units have to be the same thing as R. Because what's happening here is all of these units will cancel and we'll end up solving for our temperature. Okay. So in order to solve for T, we're going to just multiply 4 times 0.082 together and then divide it by that. So we'll do divided by 4 times 0.082. Divide by 4 times 0.082. That'll cancel that out. And then we just have whatever this number is equaling our temperature. And it comes out to be, we got 204.9. So you will need a calculator to do these. So you just multiply by the top and the bottom and then divide them together. You'll get 204.9. What unit is this temperature in? Well, it has to be in what? Our Kelvin. So it's 204.9 Kelvin is our temperature of the gas. So the ideal gas law isn't harder than the gas laws we've done. They just require you to make sure you're paying attention when you're putting numbers into our variables and making sure that our units are the ones that we want to match our gas constant.